Formation of stationary waves because of the superposition of two waves. I used this simulation just a couple of days back in the college, so I thought of sharing the same with others in this platform. So when you click on this, you see that this is the first wave. And when you click on play, you see that the wave is propagating towards right-hand side. And we click here, and in the same region, now the brown wave is used to indicate a wave that is propagating towards left-hand side. Now, without much of an effort, just by looking at this, we can convince the students, or we can make the students understand that yes, there are instances of time where the waves seem to be overlapping each other very nicely. And there are other instances of time where the same, where the wave seems to be completely out of phase. I'll just pause it here and we will move it step by step. So here you see that waves at this instant, they are completely overlapping each other. And as you let the waves progress in their respective directions, we see that we arrive at an instant where one wave is exactly opposing the other wave. So this is what I used to describe. And here comes the resultant wave, and now we can see that. So without having to sweat over it much, we can make the students understand why the blue wave and the brown wave, based on the colors that I have used here, are called progressive waves, and why the resultant wave, which is indicated using the red color, is called as a stationary wave. And how are the loops formed? Here are the loops which are indicated with red dotted lines. And how are the nodes and antinodes formed? Not only this, the students generally have a doubt as to why is the condition required that the amplitudes have to be same. What happens if the amplitudes are different? Well, let us do that and see why the amplitude should be same. I'll pause this here. I will hide the nodes and antinodes. I'll hide the loops. I'll hide the resultant wave. And I'll keep these two waves as it is. Now I'm increasing the amplitude of the wave that is going to propagate towards the right-hand side, which is indicated in blue color. I hold it at 80. And I decrease the amplitude of the other wave, which is going to propagate towards left-hand side, which is indicated by brown color. So it is 80 and 40 now. Now let us see what happens. You see that the waves are propagating. And even before I show the stationary wave, it is evident that the waves are not exactly canceling out each other. And that is what is seen by the resultant also. So the student is himself able to see that if I hide wave 1 and wave 2, this is not a stationary wave. You see, there it slides forward, and there it slides forward towards the right-hand side. Okay, so this was as to what happens to the resultant wave when the amplitudes are not same. So now let us bring back the amplitudes to equal values. I'll fix them at, I think 60 should be fine. So I'll increase this also to 60. And now we will try to understand the importance of the second condition as to why should the frequency be same. So what I will do is I will increase the frequency of one of the waves, that is the blue one, up to, let us say, 280. And I'll decrease the frequency of the other one, the brown one, to about 160. And here you go. There is no nice overlapping anywhere. There is no complete out of phase anywhere. And that is what is seen in the resultant wave also. Now, if I hide W1 and W2, you see what kind of a resultant wave is formed. So that is clearly evident just by the visual effect of it that it is for this reason that the resultant wave cannot be called as a stationary wave. And naturally, when it is not a stationary wave, you can keep clicking on this loops button or nodes and antinodes button. You won't see any nodes and antinodes formed because it is not a stationary wave. So I hope you like this, and this is how I use these simulations in my contact classes and my online classes also.